It is one of the most complex and sophisticated scientific instruments ever built. It is orbiting our Sun 1 million kilometers out in space in temperatures of -266 degrees Celsius. It is a time machine that will peer deep into the past and reveal unexplored reaches. And it will be our key to understanding where we fit in this enormous universe. Launched aboard an Ariane 5 rocket, the James Webb Telescope has successfully reached its destination, unfurled, and begun its great adventure.
Hubble revolutionized astronomy. Hubble showed us the early universe. Hubble showed us what the universe works like. And as these revolutionary findings came along, people realized we need a next generation space telescope. This was 25 years ago, and this is how Webb came into being. Now, you can see 25 years of development time. This is not unusual for a large space mission, from the first idea to fruition, to the launch. And this is why these missions are really once-in-a-generation launches. We are witnessing something particularly special that an astronomer typically gets to witness once, if they are lucky, twice in their entire career.
James Webb Space Telescope is a collaboration between NASA, ESA and the Canadian Space Agency. So altogether that's 24 countries, lots of industrial companies, academic institutions, universities, and thousands of scientists across the whole world are now waiting to use the telescope. So by combining the power of the best in engineering and science from all of those countries in this international collaboration, we can do much more together than we could do on our own.
The origin of Webb is the search for our origins. We want to find out where the first galaxies formed, how they formed when they started making their stars in the very early universe not long after the Big Bang. And to do this, Webb uses its big mirror and its infrared vision to look into these really early days, observe the light from these galaxies that's been traveling to us for billions of years, and it shows us these galaxies how they were billions of years ago.
Sure, so infrared is a longer wavelength than visible light. So we can't see infrared, but James Webb can. And what's important about an infrared telescope is it allows us to see through clouds of gas and dust and see the planets and stars and galaxies that are beyond. In addition, James Webb has a larger mirror than Hubble, so it can see back further in time, and it's orbiting at a different point.
James Webb is very complementary to everything that has been done before, to Hubble, to Herschel, but will be a huge step forward just because the collective area is huge. 6.5 meter is pretty impressive. Hubble, as a comparison, was 2.4. So we're talking of a collective area which is much bigger, much more sensitivity. We say 100 times more sensitive. With a complement of state-of-the-art instruments which will take images and spectra in wavelength regimes that we haven't explored as much from space up to now.
The telescope houses 4 scientific packages: MIRI, a mid-infrared instrument, the near-infrared NIRCam, NIRSpec, a spectrographic analyzer, and the NIRIS imager and guidance sensor.
The near-infrared spectrograph, or NIRSpec, it's one of the 4 scientific instruments that we fly on James Webb Space Telescope, or Webb Telescope. It's very important because it will allow us to analyze the light of the astronomical objects we will observe. A spectrograph works very much like a prism. In fact, there's a prism inside our instrument and gratings, and they, like the prism splits the white light into its rainbow colors. This instrument will split the near-infrared lights from the astronomical object into its components. And this is very useful to scientists because from that they can understand the physics of the objects they are observing, what are the temperature, the elements, the physical condition, and therefore we can understand what's going on the objects we observe. So we will observe all sorts of astronomical objects, from galaxies, and the focus is very much on very far away galaxies that are 13 billion light years away from us, so back in the far past, that they were forming soon after the Big Bang, from very what we call nearby objects, which are not really nearby, but they are exoplanets in stars around our neighborhood, the neighborhood of the solar systems in our galaxy. So this is the type of objects we will observe, and investigations. It's about understanding what are the atmospheric condition on the exoplanets, or what are the physical condition of the galaxies we observe far away. So, going back to the very far away galaxies, this instrument NIRSpec will play a crucial role in the, observing this far away galaxy and telling us what is the physics. So again, what are elements are present, in which proportion, what are the temperature, and that is fundamental if you want to understand how galaxies form, which is one of the big questions we have in astronomy. We see trillions of galaxies around us, how all these galaxies formed, and with this instrument we can piece together more of the puzzle. It complements the other instrument because of its function of a spectrograph. So on the Webb telescope we have cameras, other type of spectrograph, one particular MIRI, which is also a partially European instrument, which will focus on the mid-infrared light. Near-infrared is the focus of NIRSpec. Analyzing the light that comes from astronomical objects in the near-infrared wavelength range. While with the camera we see images, so we detect the objects and we know where they are and what are the main characteristics. With NIRSpec we focus really on certain objects and analyze the lights and split the lights into its components, and with that understand the physics of the objects we are observing.
The telescope is in a halo orbit at the L2 or second Lagrange point and is orientated away from our Sun, with the sun shield keeping the instruments at their very low operating temperatures.
Where is the telescope pointing relative to the spacecraft? So we waited for the near-infrared camera to get the detectors cold enough so that we could take the images, and we did some evaluation of that. And once we were convinced that it could take images, we were really trying to determine if we pointed at a bright isolated star, where's the telescope pointing? So we picked a star that was very bright and didn't have any stars near it that would contaminate the image. We know that the primary mirror segments aren't aligned yet, so they actually act like 18 separate telescopes, and we expect to see 18 separate images, one for each mirror, that are a little bit blurry at this point because we haven't aligned or focused anything. And so we pointed at a bright star and we made a mosaic. We actually took the near-infrared camera and we took images in different parts of the sky, and then we looked for the 18 spots from the 18 different telescopes, if you will, and we were very excited to find them. They were actually very close to where we were pointing, well within our expected size of where they might land. and the 18 spots were actually fairly close to each other as well. So really everything was very close to what was predicted and much better than what we considered to be the worst case pointing. So we were really excited about that.
Over the following months, each individual mirror was adjusted and focused, then aligned together to create one single image. The alignment image of the single bright star gave an indication of the power of the Webb telescope. As seen here, behind the bright star, the image captured numerous distant galaxies. The science team then captured several sample images of different objects.
The first images from the James Webb Space Telescope are designed to demonstrate the full range of the capabilities of the telescope.
Sorry, I'm asking the image processor.
Scientists then sat down and studied these many test images, which amazed the team.
The cluster is, it's probably bigger than that. There's lots of light. Yeah. But I think when you stretch the background, we didn't dare to say. You should have said it. Exoplanets. Awesome. This is Iraq zooming from the 70s into the 80s and 90s. Even in NIRCam, right? It really stays the same in all wavelengths.
We're seeing a sample of the amazing science that Webb will be able to do over the coming years. Remember, it's just a sample. So we are seeing scenes and vistas from across the universe, toward the first galaxies, to stellar birth and stellar death. And we're seeing an exoplanet spectrum for the first time with Webb, showing water or steam in its atmosphere. So here, what we're seeing in this deep field image, Webb's first deep field, is a massive cluster of galaxies. And what this cluster does is it bends the light from even more distant galaxies coming behind it. And you can see that as sort of bananas or streaks in the field. And this field allows us to look for some of the very first luminous structures in the universe, the first stars and galaxies, and this was one of the reasons that Webb was originally built. So with the Southern Ring Nebula, the image here, what you see is a star that is similar to our own sun, but 5 billion years in the future when it dies. And so when stars like that die, they push off the outer atmospheres, and this gas cloud you see is filled with elements like carbon and oxygen, kind of elements that we are made of. And this is how dying stars seed the galaxy with these elements that ultimately are important for the formation of life. So here we are seeing a small group of galaxies that, what we call interact, they're actually colliding with each other. And this is a very fundamental part in the evolution of galaxies. They bump into each other all the time. And when they bump into each other, they create shock waves. And in these shock waves, you have this tremendous formation of new stars. And you see these shock waves in this image here, and you see the formation of stars there.
Yes, this is a set of galaxies that are sort of locked in a cosmic dance, and so they're moving, and two of them are merging, and we can see all of them moving around in that, and their interactions.
You also see the galaxies superimposed on this field of distant galaxies in the background, whose light has probably traveled through the universe for billions of years. And so this is very typical for Webb images, that everywhere we look, we're going to have these distant galaxies in the background.
And one of the main things that we want to look at with the James Webb Space Telescope is the most distant galaxies in our universe, the furthest objects away. And that also means that they were the first objects to form after the Big Bang. The first stars and galaxies about 13.5 billion years ago. The reason that all of their light is now in the infrared is because the universe is expanding. And as it expands, the light from those most distant objects gets redshifted to infrared wavelengths. So again, Hubble can't see them, but the James Webb Space Telescope is designed exactly to see these very distant, very faint objects.
Those emission lines, yeah.
Oh yeah, this is such a beautiful image and maybe my favorite. What we see here is a stellar nursery, a cloud of gas and dust that is actively forming new stars. And you see this as sort of a landscape that looks like mountains because the cloud is being eroded away by hot stars that's off the field to the top. And they're cooking off the cloud. And as they do that, they push on it. And so what that means is that you can form new stars sort of close to the surface of the cloud there. And you can see those stars popping out. And you can see them also create jets and outflows as part of this process that move through the cloud and create these streaky structures in it.
In comparison, the Hubble imagery here captures the visible light. Now, compared to the Webb images, you can see the dark dust turn transparent, revealing what is within and behind the veil.
I'm really excited about James Webb and the spectroscopic capabilities. It's absolutely revolutionary, the sensitivity and the resolution we can get to look at the dust and the forming stars in some of the very most distant galaxies to us, where we can actually see individual stars and work out what the chemical compositions they're producing in terms of dust and the minerals they're producing and the life cycle of matter in the universe, that chemical evolution of galaxies. And no other instrument, no ground-based instrument can do this because of the atmosphere. Only space-based instruments can do this. And previously, the previous generations have been so small, they've been able to only look at galaxies in the Milky Way or in the Magellanic Clouds. But James Webb will be able to push that envelope out to lots of galaxies in the local group. And so we can look at very different formation scenarios towards the early universe. So that's what I'm most excited about, is these dying stars and forming stars.
The hope is Webb will be able to see so far back in time, it will reveal the very first galaxies and stars created after the Big Bang.
Lots of big questions. How do galaxies evolve? So the Hubble Deep Field has given us some hints of what we think is happening, but we haven't been able to see it in enough detail or with enough galaxies to really know. So it's going to fill in, almost you could think of it as a gap in time between the Big Bang and the galaxies we can study with Hubble, and we'll find galaxies that are in that gap.
This image is of the spiral galaxy IC 5332, which is over 29 million light-years away. The infrared web sees through like an X-ray into the interior structure of the galaxy.
Well, it's going to allow us to understand every phase of cosmic history for the last 13.5 billion years. So we'll be able to answer questions like how are galaxies formed and where do we fit into the cosmos. We'll be able to see the formation of stars and planets. We'll also be able to understand atmospheres of exoplanets.
The James Webb also captured images of local residents in our own solar system. Here is Jupiter seen in the near-infrared. It reveals the polar auroras and the heat signatures deep within the clouds of our largest neighbor. Here is Neptune as never seen before, its rings clearly visible along with several of its moons. The most prominent features of Neptune's atmosphere in this image are a series of bright patches in the planet's southern hemisphere that represent high-altitude methane ice clouds. More subtly, a thin line of brightness circling the planet's equator could be a visual signature of global atmospheric circulation that powers Neptune's winds and storms.
I think the great thing about Webb is that it actually touches all of astronomy. So because it's so flexible, you can use it to study things inside our own solar system, but you can also use it to find examples of the very first galaxies. So it really is spanning almost the entire history of the universe. So it's really going to be transformative to lots of different areas. I think the two areas that are going to be transformed the most are my own field, which is finding and understanding these very early galaxies, and then on the other end of the scale, actually looking at planets around other stars that are relatively nearby to us. But I think every single astronomer in the world will ultimately be taking some of the results from Webb and incorporating it into their own research.
Astronomers have made giant steps in our understanding of the universe over the past decades, but there remains much to learn about our cosmic origins, and the range of questions waiting to be answered is causing high expectations.
Webb is more than tens of thousands of scientists. Webb is 8 billion people looking for the origins.